We turn our attention now to a group of objects in the outer solar system that are sometimes overlooked. These are the large Jovian moons. These moons illustrate a great variety of features and landforms that were quite unexpected until we got a close-up look at them. And this really only became possible when our spacecraft again visited the outer planets, as we mentioned in the previous lecture, the Voyagers, Cassini, and Galileo. Scientists had expected fairly simple worlds because these were relatively small bodies, and yet they weren't for quite a surprise. The spacecraft showed us amazing images that we had never expected of the surfaces of these particular bodies. Well, one very important fact that we must keep in mind when investigating these bodies is that being in the outer solar system, they have considerable amount of ice in their compositions. Generally speaking, we think of them as having approximately half ice and half rock. So this makes them very different bodies than terrestrial worlds, as we're going to see, and it enables different processes to occur than might occur on the terrestrial worlds. So we're going to begin with Jupiter, and then we'll move outward through Saturn and Uranus and Neptune. But we're going to do more than simply just describe what we see on their surfaces. We're going to identify and uncover a very fundamental, important process that occurs on these moons in the outer solar system that really wasn't expected very much at all, again, before we got a close look at them. So let's begin with Jupiter. You might recall that Galileo even saw 4 moons orbiting around it with his small telescope. Well, our spacecraft have revealed them in all their glory. So let's take a quick first look, and then we'll look at them each individually. First of all, here you see Io, Europa, Ganymede, and Callisto. And interestingly, each is its own very unique world. Their density, that is the amount of rock versus ice, and their geologic activity all decrease with increasing distance from Jupiter. Now, this isn't just a coincidence. There's a very definite reason for this. Io, the innermost moon, very active volcanically, a major surprise. Europa shows a very smooth, icy shell. Ganymede, a wide variety of different terrains. And finally, Callisto shows heavy cratering. Let's go ahead and take a closer look at each of them. Here you see some dramatic images returned by our visiting spacecraft. On the lower left and lower right, these are early images from the Voyagers that show actual volcanic explosions occurring on Io. And again, this was not expected, as these are relatively small worlds and, as we described earlier, would not have much internal heat to drive this activity. You see the other pictures, close-ups from the Galileo spacecraft, clearly show dramatic evidence of this volcanism as well. How can this be? Well, it begins when we consider Io's orbit. Being close to Jupiter, it of course would feel a strong gravitational pull from Jupiter, and yet Io's in an elliptical orbit, meaning that sometimes it's a little closer to Jupiter and sometimes a little farther, and as a result, sometimes feels a stronger pull and sometimes a weaker pull. Well, this difference tends to stretch Io and then release it, and stretch Io and then release it, and stretch Io, and so forth. This causes tremendous friction inside of Io, which generates tremendous heat. Sooner or later, that heat must escape through the form of volcanism. So this tidal heating is a new process that had not been seen elsewhere in the solar system until there it was staring us at the case of Io. Why doesn't Io simply drift out of that elliptical orbit? Well, because it simply cannot. It is constrained or held into that orbit by the other Jovian moons, Europa and Ganymede. So we see a case here where tremendous energy is essentially pumped into Io, and that energy essentially escapes as active volcanism. To this day, we continue to monitor active volcanoes on Io. Moving on to Europa, we find a very smooth surface here of ice. Very few craters, if any, telling us it's a very young surface that's been resurfaced, very much like sea ice on Earth. In fact, we think it very likely that beneath the ice, there likely is an ocean of liquid water. How can this be in the cold depths of space? Well, this ocean would be kept warm and liquid, again, by tidal heating from Jupiter. Europa also moves a little closer and a little farther from Jupiter, receives this tidal heating, although not as much as Io, and as a result, this heat keeps some of that ice as liquid water. You see in our image here a number of large brown cracks. This is where the ice cracks open. Fresh material from beneath now can reach the surface as the cracks spread apart, and then as Jupiter's gravity changes, the cracks are pushed together. And so you get, frankly, a jumbled mess of ice on the surface, as you see in our close-up images here. So scientists are very excited that Europa likely has this ocean of liquid water. Recent discoveries indicate there may even be a way to sample that water as it escapes the surface of Europa. Ganymede, the third moon out, is the largest of the Galilean moons and largest one in the solar system. Here we see a tremendous variety of different types of landforms, indicating different processes over time. We see early cratering, some areas more heavily cratered than others, indicating different ages. We see evidence of past tectonics, past volcanism. However, with no atmosphere, we would not see any signs of erosion. So a tremendous variety indicates that Ganymede was likely an active body for a considerable amount of time, again with some areas being resurfaced and changed and distorted, perhaps covered over by various types of volcanism. So a very fascinating world here as well that has quite a detailed and complicated story to tell us. Finally, Callisto, the fourth moon out, is much more what we might expect. Relatively simple, relatively heavily cratered, indicating that the surface has not changed very much over the many millions of years, but instead a fairly straightforward surface that again retains much of the cratering from its early ages. Now we do see a number of white or bright colored craters. Why is this? Well, as with the other Galilean moons, when there are the occasional impact over long periods, much of that surface is icy, and as a result, fresh, brighter ice is exposed than the older, darker ice that has been slowly darkened over time. So a less complex world, really essentially very little, if any, tidal heating, very little volcanism and tectonics mean that Callisto is a simpler world. So here in the Jovian system, we saw really again a model of more activity the closer the satellite was to Jupiter than farther. We're going to watch for that as we move on now to Saturn. Saturn has a number of different moons, one large one in particular that we're going to look at, Titan, and a number of other medium-sized moons. Now Titan is a very unique case. Why is that? Because it is the only moon in the solar system with an atmosphere, and that makes it a very special body for us to explore. The other moons don't have that, although they do show some interesting features, as we'll see. Interesting at Saturn, we don't see this steady progression of less activity the farther out we go. Why is that? Well, because again, we don't have the very simple, straightforward relationship here than we did at Jupiter with its 4 moons. However, we will see significant evidence of tidal heating. So Titan's thick atmosphere essentially covers the body and blocked our view when the Voyagers first flew past years ago. They really couldn't see anything of the surface, and this of course greatly limited our knowledge of it. Well, years later, when we were planning to send a follow-up Cassini spacecraft, they made sure to include radar systems that would be able to look through that haze, look through that atmosphere, and see the surface features. Better yet, NASA teamed up with the European Space Agency to deliver aboard Cassini a European probe that would enter the atmosphere of Titan, deploy a parachute, and drift all the way down to the surface, all the while taking images and other measurements. So what a dramatic mission this was, the Huygens probe to Titan. Happy to say it carried out successfully. We got very dramatic images of Titan, the descent through the clouds, and the view as it appeared. let's have a look at what it actually did see here. Our left-hand image shows a view from approximately 5 miles altitude of a broad region that's somewhat higher than average. We see no craters, indicating, again, a very young surface. The lower part of the image shows us a little darker area that's much lower in elevation. And it became clear to scientists that what we had here essentially was a drainage area. Liquid methane from the higher regions is slowly draining down into this lower region on the left, filling it in somewhat as a lake. And interestingly, the Cassini orbiter, with its radar systems, has been able to look down on Titan and over time piece together views of exactly this, lakes here on the surface of Titan. Well, the probe did successfully reach the surface, and on the right you see the very dramatic image from the surface. Near true color here, we see methane blocks of ice. Essentially, when the spacecraft landed, it felt kind of a soft surface, very much like wet sand, telling us that the methane here can exist in frozen form, or in liquid form, or in gaseous form. So a very, very different world than we are used to here on Earth, Saturn's moon Titan. Moving on, Saturn also has a number of other moons. You see briefly here tiny Mimas with one large crater, but Enceladus has attracted much attention in the last few years as the, again, Cassini spacecraft continues to get close looks at it. At first you do see a few craters there, don't you? But notice in the lower left part of our main image some mysterious long narrow channels, essentially cracks or grooves in the surface. What's going on here? Well, here we have ice volcanism. In other words, Enceladus, being very small, is subject to tidal forces from Saturn that again have essentially generated heat inside of it. This heat eventually wants to escape. As you see on the right-hand image, the Cassini spacecraft actually was able to take a picture of some of this water vapor or frozen ice spraying out of these huge cracks. Of course, much of it would be deposited back down onto the surface and fill in any craters. And so we have a very young surface here. In fact, in a dramatic, bold move, they literally positioned the spacecraft to fly right through one of these ice plumes. And direct sample indicated it was almost pure water. So a fascinating discovery here by the Cassini spacecraft that Enceladus, a very small moon of Saturn, has these dramatic ice volcanoes. You see a few more close-up images here taken by Cassini showing that this geologic activity is ongoing. So once again, a significant surprise for us here, a very small moon. We might not expect such activity, and yet there it is. Saturn also has its moons Tethys and Dione, as you see here, each with their own particular features. Tethys having a tremendous rift system that stretches most of the way around the moon. Dione has bright regions as well, where ice, again, is escaping and coloring the surface, so to speak, and yet being heavily cratered, we would consider that an older surface as well. So, again, a variety of landforms here. We don't have every detail ironed out, but we are learning so much more from the Cassini results. Saturn's moon Iapetus, another dramatic story to tell. You see these very interesting images here where one part of the moon is very dark and one part very bright. How would this happen? Well, it turns out as Iapetus orbits Saturn, the leading edge of the moon is essentially passing through a region where there are some dark particles that have been ejected by other moons. And this dark material begins to build up and to accumulate and to get darker. And as a result, when sunlight hits the darker material, it warms up somewhat. And as a result, any ice in those regions begins to sublimate or to vaporize away. Where does that ice go? It essentially travels around the moon, not only to the polar regions, but to the trailing side. And here it can accumulate in a brighter region. And of course, the more time that goes on, the more this process occurs. Darker material is swept up, warming the leading edge. Much of the water vapor and ice is now condensing out on the trailing edge of Iapetus. So we get a very dramatic difference in albedo, or brightness, from one hemisphere to the other. So quite a variety of moons here within Saturn's system, but let's move on to those of Uranus. Uranus lacks a very large moon, but it does have 5 medium-sized moons that we're going to look at, and again see some very interesting features. Its moon Miranda in the center is quite small, and yet shows signs of dramatic geologic activity. Difficult to explain some of the features we see here. A jumbled terrain with huge towering cliffs. Clearly such a small moon could not have generated this activity on its own. Well, it's a difficult puzzle for scientists to solve, partially because we only have a limited number of images of these moons. But there's a hypothesis that perhaps even Miranda might have actually been broken apart at one point in time and then reassembled later on, resulting in what we see. You notice aerial surface with some deep canyons, very long, very broad canyons, indicating some activity there in the past. Umbriel we don't have such good images of, but we generally see a heavily cratered region indicating an ancient surface. Titania, again, some evidence of past geologic activity, although not so much today. We do see some canyons and ridges indicating possible tectonics. Oberon primarily cratered with some brighter regions as well. So again, quite a variety when we look at the moons of Uranus here. Much to be learned. Unfortunately, again, only a limited number of pictures, as only one spacecraft has visited. Well, we finish then at Neptune, and besides a couple of very small moons, Neptune's primary moon here is Triton, a very large body. Triton has a fascinating story to tell as well. First of all, we look at this image here and we see 2 different types of terrain. Towards the left there, we see a very smooth region with very few craters. Very interesting texture. It's come to be known as the cantaloupe terrain because it's very much like the surface of a cantaloupe. On the right, you see what is essentially a huge polar cap. Why would it have such a large polar cap? Well, start out with the fact that the tilt of Neptune is considerable, approximately 29 degrees. But then as Triton is orbiting Neptune, it also is tipped over another approximately 30 degrees. And as a result, Triton's axis is tipped approximately 50 degrees to the plane of the solar system. Well, you might recall this tilt is what causes seasons even here on Earth, so Triton experiences very extreme seasons. And as a result, for many years, one particular hemisphere is in the sunlight, and for many years one is not. It's in the darkness. Now add to this the fact that the orbit of Neptune around the Sun is quite long, 164 years. You can see that Triton is going to experience extreme seasons for 41 years. Well, you can imagine that, again, the hemisphere in the sunlight is going to warm up, and much of the ice there is going to vaporize or sublimate and migrate to the darker hemisphere where it will be deposited as a polar cap. But as Neptune and Triton circle the Sun, these regions come into view. Now the reverse takes place. The polar cap in the sunlight begins to warm, begins to sublimate, and this reverses. This material now migrates to the other pole. You can imagine, obviously, that quite a bit of it may condense or precipitate out in the equatorial regions to create this cantaloupe terrain. Well, here Voyager 2 came by and saw Triton essentially at this this time of change in its seasons. We see the polar cap, but notice the dark streaks here. The dark streaks are where some of this sublimation is happening. It's not perfectly uniform. We get areas where it's more intense than others. And the reason that they're elongated is because this material, as it rises up above the surface, forms a very tenuous, very thin atmosphere with gentle winds blowing it in a particular direction. So quite an interesting situation here. The extreme tilt and the long orbit conspire to show us a world where much of the surface material migrates back and forth, creating a very interesting type of terrain. Well, there's one more fascinating piece of information here regarding Triton, and that is that its orbit is decaying. it is slowly, gradually getting closer to Neptune. Why is that? Well, one of the first clues was that it actually begins with the orbit itself. Now, we mentioned early in our course that nearly all bodies in the solar system orbit the sun in the same direction, and they spin in the same direction. Triton is an exception. How could it possibly be an exception? Well, this indicates that it likely did not form around Neptune, but rather was captured. As we're going to see in our next lecture, there are some bodies in the outer solar system approximately this size, such as Pluto, and it seems likely now that Triton probably at one time was also a free body, and yet got too close to Neptune and was captured by the tremendous gravity of the giant Jovian planet. Well, since it's in a retrograde or backwards orbit, again, it is slowly decaying, getting closer and closer, and someday if it gets close enough to Neptune, it likely would be broken apart. So again, what a dramatic story that Triton has to tell. Well, I think you've seen quite a variety of moons as we explored the outer solar system here. Our spacecraft is giving us beautiful images, but there's one very interesting question that we're going to close with. We saw earlier that smaller terrestrial worlds are less active geologically than larger ones. And again, we explained that that was due to their internal heat. Well, how is it then that these small Jovian moons can be more geologically active than even a moderate-sized terrestrial world, perhaps Mars? Well, I think you saw part of the answer. Tidal heating from the large Jovian planets essentially generates heat within these moons, and that powers the activity. But there's a second factor, isn't there? We said at the outset that these moons are approximately half rock and half ice, and as a result, that ice can melt easier than rock, and it requires less energy, less heat to generate the volcanism. So yet again, a very amazing, fascinating tale here of moons in the outer solar system. Let's go ahead and summarize our discussion today. We started out by looking at the moons of the Jovian planets. We saw a wide variety of features and surfaces, but one of the key processes that we uncovered was tidal heating. Again, as a moon orbits in an elliptical fashion, it feels more of a pull and less of a pull from time to time. This generates internal friction, which results in internal heating, which results in activity. And so we saw, again, a wide variety. Io, Jupiter's innermost moon, extremely active even today. Enceladus, a moon of Saturn, very active today. Others show signs of very young surfaces, meaning that tidal heating has affected them as well, even if we don't see it active today. We visited briefly Saturn's large moon Titan, fascinating world with an atmosphere. We've actually landed there and taken close-up images. So much more to be learned about it and the other moons. And then we saw Uranus and Neptune as well, having quite a variety of features on their moons, indicating widely varying histories. We haven't quite untangled every detail there yet, but time will tell. So I hope you enjoyed our visit to the Jovian moons. Next time we'll pick up by looking at very small bodies in the outer solar system, comets.